We now ask what's going to happen if the object, the 1.33 kilogram object, attains the velocity 5.1 meters per second at the end of the rubber band, and somehow the rubber band is suddenly snatched out of the way or dissolves or disappears or something, and the object continues to slide along a level surface, horizontal surface, where the coefficient of friction is 0.04. The question is, how far will the object travel before it stops? So the initial velocity is 5.1 meters per second, final velocity is 0. What's our delta S from here to here? Okay, the 1.33 kilogram object has a weight of 1.3 newtons. When that's multiplied by the coefficient of friction, 0.04, we get the frictional force, 0.04 times 1.3 newtons. The 1.3 newtons is the force that's holding the object to the surface, or the force between the surface and the object, whichever way you want to look at it. When we multiply that out, we see that the force exerted by friction is 0.052 newtons. Now the object has a kinetic energy here. Kinetic energy being the 3.4 joules that we found previously. If we do the 1/2 mv squared for this mass and this velocity, of course, we get that 3.4 joules. But we've already figured the 3.4 joules. That's the energy that was imparted to the object by the rubber band. So the situation is this. The object has to exert a 0.052 newton force against friction. Since friction is pushing it back with a 0.052 newton force, the object has to exert a 0.052 newton force against friction, and that's going to dissipate the kinetic energy of 3.4 joules, which can of course be gotten by taking 1/2 m v0 squared. And notice that v0 doesn't stand for the v0 of the previous part of the problem. It's the initial velocity for this part of the problem, the 5.1 meters per second. That was the final velocity before, but now we're in a new phase. It's the initial velocity now. In any case, if we take that v, square it, multiply it by the mass, take 1/2, we get the 3.4 joules, as we must. So that the work done, F delta S, against friction is 3.4 joules. So delta S is 3.4 joules divided by the force of friction, which is 3.4 joules divided by 0.052 newtons, or about 68 meters. So the object will travel 68 meters roughly. As an alternative, if the work done plus the kinetic energy equals 0, now this is the work done by the system, by the object as it slides across the table, or whatever it's sliding upon. If this is the work done against the friction, in this case, plus the change in kinetic energy, plus the change in potential energy should equal 0, according to what we've seen before. In this case, the change in potential energy is 0, so just the work done against friction in this case, plus the change in kinetic energy has to be 0. What's the change in kinetic energy? Well, the kinetic energy here is 3.4 joules. Here it's 0. The kinetic energy drops from 3.4 joules to 0. That's a change of negative 3.4 joules. That's the change in kinetic energy. The F delta S, then, plus a negative 3.4 joules has to equal 0. And if we add the 3.4 joules to both sides, and it's got a negative on it for some reason, let's just make that positive, because when it goes over here, it, of course, becomes positive. Solving for delta S, we just add the 3.4 joules to both sides, divide by F, and we have the same calculation we did up here, and again we get our 68 meters. This alternative makes use of this formalism, the work done by the system, plus the change in kinetic energy, plus a change in potential energy, where the work done by the system is the work done against non-conservative forces. Change in potential energy is the work done against conservative forces. This is what we get. Last part of the problem. If the object starts with a velocity of 5.1 meters per second, the velocity that it obtained from the rubber band and slides up an incline. Now we assume a frictionless incline this time. We could add friction into the equation here, but to keep it fairly simple, we'll just do the frictionless case. The question is, how much higher will it be at the end? In other words, how much does its altitude change, and how far along the incline does it travel? We note that we have an initial kinetic energy of 3.4 joules. If the object travels till it stops, its final kinetic energy will be 0 because its velocity will be 0. So we have a kinetic energy change again of negative 3.4 joules. Now, since there's no friction, and as a result the delta W against frictional or non-conservative forces is 0, then we can say that the change in potential energy plus the change in kinetic energy has to be 0, which means that the change in potential energy is the negative of the change in kinetic energy, which is the negative of our negative 3.4 joules. Put a decimal in here. This means that the potential energy will be 3.4 joules. Another way of looking at this simply is that the potential energy increase of 3.4 joules will decrease the kinetic energy by 3.4 joules. So the change in potential energy, which is equal to the work done against gravity, is the weight of the object times the delta Y. Work done against gravity, of course, you have to exert a force equal to the weight and through a distance delta Y, which is your change in altitude, and that's equal to mg times your delta Y. So, mg delta Y is 3.4 joules. We solve easily. Delta Y is 3.4 joules over mg, which is 3.4 joules over 1.3 newtons, the weight of a 0.133 kilogram object, and we get 2.7 newtons. To get the delta S on the incline, we note that delta S times the sine of 5.2 degrees, just using the simple trigonometry, equals 2.7 meters. So the delta S is 2.7 meters divided by the sine of 5.2 degrees, or approximately 30 meters. And of course we can see the triangle that we have here, the 5.2 degrees, the delta S being the hypotenuse, delta Y being the opposite side, means that the sine of 5.2 degrees is delta Y over delta S, so that delta Y is delta S times the sine of 5.2 degrees.